Good evening, everyone. I hope I'm audible to you all. Okay. I'm Chamini Veerasinghe, an undergraduate of Sabra University of Sri Lanka. So it's my pleasure to have you all in this session today. So first of all, I would like to welcome you all to the Bootcamp for NASA Space Apps 2022, powered by SEDS Sabra in collaboration with SEDS Sri Lanka. There's always light if only we are brave enough to see it, if only we are brave enough to be it. With that, we'll go ahead. So now I'm going to give you a brief introduction of today's session. I hope that you already know about the annual webinar series by SEDS Sabra. So just as that, today also we have this boot camp for NASA Space Apps, which is also basically designed for dynamic individuals like you who are willing to represent Sri Lanka in international platforms. So if you are such a devotee, just stay connected with us because today's session on approach of application of gravitational waves to investigate the parameters of proton neutron stars of supernova explosions will also surely be a very fruitful, effective, and also an informative session. So today, Mr. L. Malik M. De Silva, a lecturer in physics of the Department of Physical Sciences of the Faculty of Applied Sciences of Sabra University of Sri Lanka, is going to share his precious knowledge with you all. Before moving to the session, I would like to inform you that at the end of this session, you will get time to get clarified about all your issues regarding today's topic. So I'm not going to speak more and we'll move to the valuable session which you all have looked forward to. So I would like to hand over the session to today's resource person, Mr. Malik M. De Silva. So sir, it's over to you.
Okay, thank you very much. I would like to thank SEDS Sabra inviting me as a speaker in this event. So I would like to share my knowledge in my best. Now I'm going to share my screen. Can everyone see?
Yes, sir.
Okay, good evening, everyone. I am Malik M. De Silva. So today I'm going to discuss with you about the approach of application of gravitational waves to estimate the parameters of proton neutron stars of supernova explosions. So before moving to this session, I would like to give a brief explanation about me. So I'm El Malik Madhushankar De Silva. So my hometown is Balapitian Gold District. So I school attended to Revata National College and I did my A-levels in 2008. And I got my bachelor's degree in physics in the Sabra University of Sri Lanka. And then I studied master's in the Nagopa University of Technology in the field of gravitational waves. And currently I'm reading my PhD in the same university. My current position is lecturer in physics as in the introduction session. So before start the session, I would like to give a brief introduction regarding the astronomy. As all we know that everyone very much interested on sky observation. I think everyone experience in the night sky observation in their childhood. So when we consider about this history, it goes back thousands of years. So we can find the first evidence in the Babylonian era, where they have charted the paths of planets. These are some evidences for that. So even though we consider such ancient era, scientifically the first observation was performed in 1610 by great astronomer Galileo Galilei by using his own telescope. So anyhow, the new sophisticated era was started in 1990 after the launching of Hubble telescope, where they have used some different bands of electromagnetic radiation to observe the universe. Already this has served us around 30 years, and this has revealed so many mites in the universe. So, as all you know that very recently, the James Webb Telescope launched. So now it's in the tuning process. I believe that much more mites will be revealed by using this James Webb Telescope in the future, because the expectation of this James Webb Telescope is to go to the era of Big Bang. So therefore, we are waiting for so many information regarding how the universe is evolving and what are the things that happened in the past in the universe. So before the 19th century, people were very much interested on sky observation by using telescope, which means by using the radiation of electromagnetic. So, but there was a problem, as all we know that when we consider about very much far away. So very much far away objects from our Earth, it's quite difficult to observe by using telescope astronomy, because some electromagnetic radiations could be absorbed by interstellar objects. And there is one another disadvantage of this electromagnetic radiation or telescope observation. As we said, when we consider about binary black holes or neutron stars, those are the end product of stellar objects. So therefore, if we need to understand about the evolution of the universe, we should study about these black holes and neutron stars. So therefore, studying or detection of these binaries or black hole or neutron stars is very important. But the problem is that excuse me, it's quite difficult to conduct the session if you make some noises. Sorry. So let's go forward. So as I mentioned you earlier, if you want to understand the evolution of the universe, the most important things are black hole and neutron stars. So therefore, by using this electromagnetic radiations or telescope astronomy, it's exactly difficult to observe those black holes and neutron stars. As you know that because of this high gravity nature of this kind of compact objects, it's difficult to see or observe these objects by using electromagnetic radiation, because light is also absorbed by this kind of binary or compact objects. So therefore, we should find another way. So Albert Einstein showed a new path, which is the gravitational wave observations. So these are the new era to investigate or understand the evolution of stellar materials or stellar matter in the universe. So therefore, now we are very much concerned on gravitational wave astronomy. So now I'm going to explain you about the gravitational waves. So when we talk about gravitational waves, there is a very much important term which is called as space-time. So before the 20th century, people think that space dimension and time dimensions are independent things. These are not dependent on each other. But in the general relativity, Einstein showed a conceptual models that combines 3 dimensions of space and 1 dimension of time as a one quantity. So conceptually, actually, it is it's like a fabric. So therefore, we call it as a space-time fabric. In this case, you can see that it's a kind of a stretch cloth. So by using this conceptual model, we can explain actually 2 things. One is the gravitational field, and another thing is the formation of gravitational waves. So in the case of classical mechanics, the scientists and people think that the gravity is a kind of attraction between 2 objects. But in the case of general relativity, according to this conceptual model, we can consider that how much the objects deep in this fabric is the amount of gravity of that object. It means that the high gravity objects much more deep in this space fabric than low gravity objects. So, and also by using this fabric, we can explain how gravitational wave propagate in the universe. So, when we consider about the objects with quadrupole moment, which can form gravitational waves. So, in general, I can explain it like this. If there is an accelerating car, which also can produce a gravitational wave. Even our body also can produce a gravitational wave when we are running or when we are moving or when we do kind of activity. But the problem is that such gravitational wave, the amplitude of such gravitational waves are very, very much low. So therefore, those are not that much important to detect or for using some applications. So again, I'm going to little bit explain about the quadrupole. So if we consider about the quadrupole, which represent how stretch out along some axis the mass is. So the better ways explanation is that if we consider kind of a sphere here, when we consider about all three directions, when we consider about these three directions, if we rotate this sphere, it cannot disturb on this fabric. But when we consider about this disk, when we consider about this Z axis, what happens is if we rotate it around this axis, it cannot make a disturbance on this fabric. But if we consider this axis, it can make a disturbance on the fabric. So therefore, we say that this kind of a sphere cannot form a gravitational wave by rotation. But in this case, if we consider this axis, it can form a gravitational wave. These are the fundamental things regarding gravitational waves. So, as in the case of electromagnetic waves, the gravitational waves also have some polarized components. Those are called as plus polarization and cross polarization. These two components are 45-degree angles to each other. In this animation, you can see that this is related to plus polarization and this is related to cross polarization. So in this case, this has been generated application of gravitational wave on a kind of a ring. So when a gravitational wave passes through such a ring, such a wobbling can be seen on this ring. So these are the polarization component on such a ring when a gravitational wave perpendicularly passes through that ring. So, as I told you earlier, the latest universe exploration method is gravitational wave because, as I told you earlier, if we are try to go towards the Big Bang era, so never we cannot use the electromagnetic radiation. So the best option is the gravitational waves. So as I mentioned earlier, these are the kind of ripples forming the space-time due to quadrupole dynamic objects. When we consider about the universe or space, there are basically two sources to generate gravitational waves, space gravitational waves especially. So those are binary stars and co-collapse supernova. So in the consideration of binary stars, basically there are three binary black holes, neutron star black hole binaries and neutron star binaries. Currently, all these three binaries have been detected by current gravitational wave detectors, but still we could not detect co-collapse supernova explosion gravitational waves because the sensitivity of current gravitational wave is not that much enough, and data analysis technique is also under developments. Anyhow, in the future, scientists are expecting to detect gravitational wave from co-collapse supernova as well. In this animation, I am briefly explain how actually gravitational wave is detected by a interferometer technique. So this is a brief explanation. In here, you can see that there is a binary star which is orbiting around their center of mass, and then as a result of that, some ripples are formed on the fabric, which means the gravitational waves are formed and which are propagate away from that binary. And I want to mention something. When a gravitational wave passes through some object, because of that polarization component I showed you in previous slides, that object can undergo kind of a space deformation, I mean changing of their space. So as an example, when a gravitational wave passes through our Earth, there may be a space deformation, I mean a little change in the shape of the Earth. So it's very, very small, even though you see it kind of a big wobbling, but it's very small. So this is the technique that we are going to use to detect the gravitational wave. So in here, we are mounting some interferometers on the surface of the Earth. The length of these arms are around 4 kilometers. So such a gravitational wave passes through the Earth. As a result of that, there is a space deformation, which affect to change the length of these two arms of the gravitational wave interferometer. And then there would be a path length difference in these lasers. So by using that path difference, we can get a kind of a interference pattern here. This is the basic concept, but the total mechanism is very much complicated. But basically, this is how we detect gravitational waves by using this interferometer technique. I think we can understand basically how a gravitational wave are detected by using this interferometer technique. Deeply, I will discuss within next few slides. So then I would like to explain you what are the first evidences for the existence of gravitational wave. So the postulate of existence of gravitational wave was first postulated by Albert Einstein in 1960, but it was physically detected in 2015 after around 100 years. So, but two astronomers or scientists, Joseph Taylor and Russell, proved that gravitational waves are physically existing. The way that they have used is they consider kind of a binary neutron star, and then for a long period of time, like few years, they detected this binary neutron star. Then they saw that increment of the angular momentum, and they are getting closer by rotating and decreasing the time period. So, and then depending on that observational data, and they predicted it by using the general relativity. Those observational data and general relativistic predictions match to each other. By using that, they predicted gravitational waves are possible and it exists. So therefore, they won the Nobel Prize also for this innovation. So, and then after that explanation of Joseph and Russell, the scientists very much keen on or interested on to prepare some equipments to detect the gravitational waves. So the first instrument was prepared by the scientist called Weber, so which was called as Weber cylinder, and it's called as antenna as well. So in that case, what he did was he used a aluminum cylinder with some kind of recorders around the circumference of that aluminum cylinder. He thought that if a gravitational wave passes through this cylinder, according to the polarization component, there may be a resonance like this. So, but according to this antenna, he couldn't actually identify some correct gravitational waves. According to some theoretical explanation, his observation was contradicted. So therefore, scientists tried to find a new method. This was the interferometer technique, as I mentioned earlier. So this is the current method that we are using, I mean, interferometer technique. Basically, I'm going to explain you about the working principle of this interferometer technique. Interferometer consists of the primary laser and kind of reflecting mirrors and detectors, and here beam splitter. So actually what happens initially, a laser generated the laser beam, and which comes here, and by the beam splitter, it divides into two perpendicular parts, and those move away from this beam splitter like this. So the reflected mirror sets 4 kilometers far away from this beam splitter, like this, and then these two components once again reflected back from these in mirrors and come here, and then finally it is detected by this photo detector. So as I mentioned you in that small animation, if there is a gravitational wave, I mean if a gravitational wave passes through the Earth, there would be a length difference in these two arms. So therefore there would be a path difference in this reflected beams. So which is detected as the interference pattern on this photo detector. This is the fundamental method of detection of gravitational wave by using interferometer technique. So by using this animation video, I'm going to explain you much more how gravitational wave are detected by using a interferometer. Beam split and then come back. If there is a gravitational wave, there would be a path distance difference, and then it's detected. So, and then you can see splitted, it splits the beam and then reflected back by the end mirrors, and then finally it comes to the photo detector. In here you can see that constructive interference. Nothing can be seen because these are yes. If there is a path difference, these are some constructive interference patterns as a result of the change of the distance of these arm lengths. So this is the basic method of detection of gravitational waves by using interferometers. Even though we consider this interferometer technique, actually it's very, very difficult. So why I'm going to say like that? So when we consider about this gravitational wave, there is a very important factor which is called as space dimension changing factor, or strain. This is very important term in the gravitational wave detection, strain. So if we consider a binary system like this, it can produce a strain. By using this equation, we can calculate it. So as an example, if we consider a binary system which is 20 megaparsecs far away from the Earth, and the mass of that system is 10 solar masses, it means its mass 10 times larger than our sun. And according to this equation, we can calculate the strain or the space deformation factor. It is 10 to the power minus 21. This is a unitless factor. So then by using this factor, we can determine the length change when a gravitational wave passes through this interferometer. I mean, if we consider this system, and if a gravitational wave comes from this system and it passes through the Earth, and then I'm going to show you how the arm length changes by using this kind of a system. So this is the equation that we are going to consider to find determine the length change in the interferometer. Delta L equals L into H. L means the arm length. Here, in practically, we are considering the length of arm of an interferometer is 4 kilometers, and then by using this equation, we can determine the arm length. It is 10 to the power minus 18 meters, means it's very, very small. So therefore, even though we theoretically and like in the explanation we said that this is the successful method, practically it's very difficult because the noise of the Earth surface is also larger than this. So therefore, it's very difficult to detect gravitational waves by using this technique too. So currently there are 5 gravitational wave detectors in the world, 2 in USA. These are the main 2 observatories, LIGO Hanford and LIGO Livingston. These 2 are located around 3 kilometers far away. So this is from Italy. This is the next powerful one. These 2 are the most powerful detectors in the world. GEO 600 is actually, this is a research-based observatory. Actually, this is not used for detection methods. This is for some science and development cases. So Kagra Japan is the new member in this network. So my professor also working in this Kagra Japan observatory. These are the 4 detectors that we have to detect gravitational wave in the space. So when we consider about the gravitational wave detectors, I mean the interferometers, very important thing is the sensitivity curve of that interferometer. I think you remember that I mentioned very important term related to a gravitational wave. It's the strain. Here you can see this is the strain. I mean, actually it is a kind of changing of this length. So therefore this sensitivity totally depend on that changing of the arm length. So here we are considering the sensitivity as measures the detection ability of interferometer as a function of frequency. So there are 3 things that we are considering, like characteristic strain and amplitude spectral density and energy density. So this characteristic strain is the arm length change factor. So it's very fundamental, but it is not it's no longer used to explain the interferometer sensitivity, because the thing is that when we consider about these gravitational wave detectors, the noise is very much high. So therefore this factor directly cannot be used to explain the sensitivity. So therefore the amplitude spectral density is the one that we are considering to explain the sensitivity. These are the sensitivity curves. In here you can see that actually these are LIGO and Livingston sensitivity curves. These are real curves. In here you can see that the frequency range that we are considering is from 10 to 1000. So strain changes like this with the frequency. It means this is the most sensitive point of the LIGO Livingston interferometers. It means 100 frequency events are the better events that can be detected very easily. So as I mentioned earlier, the lowest point of this sensitivity curve is the most suitable point, or the most sensitivity point of the interferometer. And then when the strain sensitivity increases, curve downs. And in here you can see that initially the LIGO start as the initial LIGO. Its sensitivity curve was like this. It was not mentioned here. This is the current one. A LIGO or advanced LIGO, and this is the next one or next development stage, LIGO A+. So in that development, they are expecting to get a sensitivity curve like this. It means, as I told you earlier, when sensitivity increases, this curve goes down. These 2 are the most sensitive interferometers that scientists are going to develop in USA, Cosmic Explorer and Einstein telescope. Now you can see that it's very much sensitive than the current advanced LIGO detectors. So I think these 2 will be open or launched in 2030. Because of the corona situation, I think it was quite delayed. Anyhow, still we are on this frequency range, I mean 10 to 100. So therefore only we can detect binary stars by using these old detectors. If we want to go to very low frequency cases, we should use some another type of interferometers, which are called as airborne interferometers. This is called as LISA. It will be launched in 2035. That is also that was also quite delayed because of this COVID situation. And by using that, scientists are expecting to go into very much low frequency cases, but the sensitivity is quite larger than, smaller than the advanced LIGO in those cases. So in here you can see that how frequency also changes with the sensitivities of gravitational wave detectors. I think now you have kind of a brief idea how gravitational wave sensitivity curves used to understanding the behaviors of the interferometer. So and then here I want to mention very important thing that when we consider about these detections, we have to have at least 2 detectors online. The reason is that if we use only one gravitational wave detector, if there is a technical error, sometimes we think that it's as a detection. So therefore, simultaneously we should use at least two detectors for the observation. So that's why at the beginning, LIGO used Hanford and Livingston 2 observatories. So by using these 2 observatories, they could be able to determine the first detection in 14th of September 2015. In both detectors, they recorded the same signal or event. So therefore, they confirm that these 2 are not because of technical errors. These 2 are the detection of kind of a gravitational wave. So in the case of observations, normally we are called as those are observational runs. Now we are in the observational run 4. These are the notations. In the case of observation run 3, we have 2 phases, A and B. These are the durations that they have used to do the observational runs. Normally, for an observation run, they use kind of a long period of time, I mean, some several months. So in the first observational run, they could only detect 3 events. So because at that moment, I mean, in the case of initial LIGO, their sensitivity was very low. So therefore, they could go only 80 megaparsec far away from the Earth. But in here, you can see there is a 10 months duration. In that 10-month duration, what they have done is they have developed, developed their interferometers, increase the sensitivity. So therefore, in the second observation run, they have increased the observational length. I mean, initially it was just 80 megaparsecs. In the second one, it was 100 megaparsecs. Likewise, now the LIGO detector can go beyond around 160 or 190 megaparsecs. It means we can detect the gravitational waves or gravitational events much more far away from. That is our expectation actually. So anyhow, these are the number of events that we have detected by using this interferometer technique. In this case, you can see that day by day, the number of events that we are detecting is increasing. So the reason is that the sensitivity increment of these gravitational wave detectors. So one thing I want to emphasize in here, even though we detect different gravitational wave events, all are binary mergers, like binary black hole or neutron stars. Likewise, only binaries we could be able to detect, because I told you that still we are concerned on the frequency band 10 to 1000. So this only matches with these binaries. If you want to go to like supernova cases, we should use another band of frequency. But currently, our gravitational wave detectors are not that much sensitive to frequencies to detect those. So in this case, you can see that the sensitivity curves or corresponding sensitivity curves for all observational runs. In here, you can see that in the very first, I mean, the observational run 1, it's the topmost sensitivity curve, and 05, that is the expectation in the future in 2025 to 2026. So this is the expected curve, as I told you earlier. When we increase the sensitivity, this sensitivity curve goes down. So you can see it here as well. So and then the first detection was done 40th of September 2015. Actually, this is 100 years after the postulate of existence of gravitational wave by Albert Einstein. So at the beginning, he told that it's wonder if we can detect a gravitational wave by using some physical equipments, because mathematically he understood that the gravitational wave amplitude is very much low. So it's very hard to determine. Anyhow, scientists could be able to avoid some barriers regarding the detection of gravitational waves. Now they have successfully detecting gravitational waves. In here, I want to mention that this is the notation for the gravitational waves, GW. Here 15, I mean first two digits represents the year of detection, and second two digit represents the month of detection, and last two digits represents the date that the object detected. So in here, you can see the publication results of the first detection. Here, this is the wavelet corresponding to the merger of binary black hole, because the first observation was the merger of binary black hole. So in the consider about the gravitational wave from binary black hole merger, there are three phases we can see. In spiraling phase, this is corresponding to this part, and then merger, and then ring down. So these are the basic phases of the time series of a gravitational wave from a binary black hole or any kind of a binary. So theoretically already we have well defined about the time series of a gravitational wave from a binary star. So therefore, artificially we can very easily prepare as a simulation this kind of binary neutron star, binary mergers. So these are the corresponding, the actual results for the detection, I mean first detection. This represents the hampered detection of gravitational wave, and this is corresponding to the Livingston. These are time series, I mean the strain versus time. So and then they have generated the spectrogram, so the frequency time plots. In here you can see that there is increment of kind of amplitude. So these are the important facts regarding the first detection of the gravitational wave. So the method that they have used is a primary solution to detect the gravitational wave is a match filtering. So in the case of match filtering, actually what we are doing is, when we consider about the gravitational wave detector output, it's a very much noisy. So this is a kind of a Gaussian noise, and the embedded signal is very much small compared to the background noise. So in here, what we are going to do is we are convolving of cross correlation our simulated gravitational wave with the output of the interferometer. If there is a gravitational wave, then if it match with the embedded signal, I mean, if this is the embedded signal and this is our simulated artificial gravitational wave, and if it's matched with this one, we can see a high signal to noise ratio. This is the just explanation for the match filtering, but there is a complex mathematics behind that. So that's why we are calling it as match filtering. Why? We are generating a simulated gravitational wave, and we try to match it with the embedded signal inside the noise of a gravitational wave detector output. So if there is a gravitational wave that matches with our artificially generated simulated gravitational wave, we can have this kind of a high signal to noise ratio in the detection. So this is the basic idea, right? But the mathematically it could be very much complex. So I told you that we cross correlate our artificially generated gravitational wave with the output of the interferometer. So in this case, how do we know the shape of the gravitational wave which is embedded in the signal and the noise? So here what we do is, it's a kind of a funny thing, we generate a template bank, because theoretically now we know the shape of the gravitational wave related to the binary merger. So therefore we consider like different masses and different distances. By using those some theoretical explanation, we produce around 100,000 of simulated gravitational waves, maybe 200,000, 300,000, it depends on the situation. So which is called as the template bank, and then one by one we convolve it with our output of the gravitational wave detector. If there is a matching one with our simulated gravitational wave, we can see a high signal to noise ratio. In this case, I'm just explaining, if there is a matching embedded signal, and then we can have a high signal to noise ratio. As in the case, in this case, you can see that no any embedded signal, only noise, and it convolve with our artificially generated wave, nothing can be seen. In here you can see kind of a peak. This is the basic idea. So therefore this take much time, I mean time consuming for this mesh filtering method, and which is very much high cost, because some high technical computers are needed, so time also consumed. Human power is also very much needed. So therefore this technique is not that much effective. So therefore now astronomers and scientists are trying to go to neural networks and some AI technologies to detect these gravitational waves which are in the output of interferometers. I think you have kind of idea. Now how do we detect gravitational wave which is embedded in the output of an interferometer? So and then by using this slide, I'm going to explain you effectiveness of the gravitational wave detection. If the detection event is very much small, so the signal to noise ratio is very much high. So therefore it's quite difficult to separately identify whether there is an event or not. If the signal is quite large, and then very easily we can separately identify there is a gravitational wave inside the output of the interferometer. So these are the basic things related to the gravitational waves. So the main topic that we are going to discuss in the today session is the gravitational wave from co-collapse supernova, because these are the future of this field. All gravitational wave scientists are now expecting to detect gravitational wave from co-collapse supernova. So therefore, there are so many simulation works now coming out from this specific field. So before explain you about the gravitational wave from co-collapse supernova, I would like to explain what are the co-collapse supernova and those things. So when we consider about the end product of stellar objects, basically we can divide it into three: supernova type AN, supernova type AB, ACN, type 2, and white dwarf. This is one kind of a categorization. There are some other categorization as well, depending on their moving path, I mean evolution path. Likewise, in here I have considered this categorization. So in here, if we consider the supernova type 1B, 1C, and type 2, those are called as co-collapse supernova. So I will explain you later what is co-collapse and what is meant by the co-collapse supernova. So when we consider about the stellar object which mass larger than 8 solar masses, which undergo with the co-collapse supernova, and the end product might be black hole or neutron star. Becoming a black hole or neutron star depend on the path. So in here, I'm going to explain you about the stability of a star and how co-collapse supernova takes place. So as all we know that there are two fundamental forces involved with the stability of a star. One is the force generated by the fusion reaction at the center of a star, and the gravity generated by that center towards the center. So these two are in a balance to each other in the stable situation. So therefore, in this stable situation, these two forces balance by each other, because the fusion reaction force in outward force and the gravity force is the inward force. These two balance to each other. So anyhow, when we consider about a star evolution, at the beginning, it's a kind of a like hydrogen cloud. So and then by the rotation, some hydrogen move at the center and increases the temperature of that cloud, and then when it becomes the considerable amount of temperature, then hydrogen fuses into helium at the center. So and then by this process, this fusion process emit huge amount of energy, and which prevents the collapse of star by the gravity. So and then after finishing off all the hydrogen into helium, and then helium start to convert or fuse into carbon. Likewise, like a chain reaction, carbon move into likewise it moves into different elements. So this is called as the onion model of a star. Anyhow, when the center of a star becomes metallic or it's totally iron, the existing temperature or pressure is not enough for further fuse these metals or iron. So therefore now the fusion reaction shuts down. So therefore no longer it cannot balance the the inward gravity force. So and then gravity force becomes prominent, and the outer layers of star infold with speed around quarter of speed of light. Now you can understand it's how much speed. So again I'm going to explain. Since fusion react stops or shuts down, the inward gravitational force no longer cannot be maintained or balanced, and then suddenly outer layers move towards the center. So this is called as the collapse. This is the core collapse actually. So and then I'm going to explain about the how what is a supernova explosion, right? This is just core collapse. So in the by using the first figure, you can understand the layers of a star at the explosion level. When it becomes metallic, I mean, this center of a mass is metallic. When it reaches the Chandrasekhar limit, this is a kind of very important term in the astrophysics. It means when the center becomes 1.4 solar masses, the collapse starts. So and then collapse means the moving of outer layers towards the center. Anyhow, now we know that the center or core is metallic, so therefore it's so much hard. So therefore, this inner falling matter bounce off by this hard surface of the center. So this bounce of nature generates a shock wave. This is the shock wave generated in by red color. You can see kind of a shock wave generated, and it moves away from the center, and this outward moving shock stalls at around 150 kilometers from the center, and it stalls around a few hundred of milliseconds when outforce from the shock and force accreted matter on the shock cone balance to each other. I mean, because of this moment of shock in the outward direction, still we have some inner falling matter, and then that inner falling matter dumped on this shock front. So finally it balances, and for a while, I mean for few hundred of milliseconds, stalls. It means stops in a particular radius, and then again what happens is still the core is getting contracted. So as a result of that, all the proton and electrons convert into neutrons. In that process, some neutrinos are generated, and those neutrinos hit this area, in this area. So as a result of that, again, some energy is provided into this shock wave, and again it expands, and finally what happens, it blasts as a supernova explosion. This is the explanation for the supernova explanation. I explain you what is the meaning of core collapse, and then what is the meaning of supernova. These two are actually two separate processes, not one. Core collapse is the first one, and then by using this shock wave, we can explain the supernova explosion. So again, I'm deeply explain you. So that, as I told you earlier, this shock stall at a one particular moment for a few hundred of milliseconds. But anyhow, because of neutrino heating, there may be some convections inside, and then this shock start to vibrate. So sometime within after 300 or 400 milliseconds, sometime it moves towards the surface of the core. So therefore, in that particular time, there would be a blast. So in this case, I mean, for the explosion process, there are three basic processes involved: prompt convection, post-shock convection, and nonlinear SASI, I mean shock instability. In the prompt convection, what happens is, as you told you earlier, shock wave initially move away from the center. As a result of that, there is a entropy gradient, and then there is a convection because of the temperature gradient, and so therefore some convections are possible. That is called as the prompt convection. And then post-shock conventions because of neutrino heating, because in this proton neutron star, all the protons and electrons converted into neutrons, and then neutrinos are generated, and then this convection layer much more heated, and then start to vibrate this, and finally it breaks. So in this simulation, you can see that SASHIO, this is the stable stable shock. Anyhow, after some convection processes starts to move, and then finally breaks. This is also kind of a related simulation work at the beginning. It's very lightly moving, but after some milliseconds, I mean 300 or 400 milliseconds, we can see the blast. So this is explained by using kind of a experimental setup. Even you can see it in your kitchen sink also. So what happens is, when water drains by this outlet, kind of a shock wave move away from this outlet, and then there is a hydraulic jump here. So this is totally related to the matter inner falling in the case of supernova explosion. So the gas falling towards the center of a star, it's related to the water flowing to this outlet, and then shock wave produced by the gas sitting on the neutron star. I explain you, when inner falling matter then bounce off by the hard core, because the core is now metallic, and then some shock waves generated. Same thing is happening here also when water moves in here, and then because of some water gathering very rapidly, some shock waves are generated, as in the case of supernova explosion. So now I'm going to explain you about the gravitational wave from core collapse supernova. So in the consideration of gravitational waves, there are two basic sources, proton neutron star and SASHI. So again, I would like to give a brief explanation regarding the gravitational wave. Gravitational wave can be generated by whatever the object or mass which having kind of a motion. So in the case of Sashi, I mentioned you that this is wobbling, or this is this oscillates. I mean, this shock wave oscillates very much fast in the last stage of the explosion. So therefore, in such oscillation, gravitational wave can be generated by this unstable shock and by the proton neutron star. In the cooling process, I mean, in the contraction of the proton neutron star, there are some 3 or 4 processes which can oscillate the proton neutron star. So because of that oscillation, the gravitational wave can be produced or generated by the proton neutron star. So in the consideration of proton neutron star, it's a kind of a intermediate state. It's not a stable state. It's an intermediate state between the supernova explosion and stable, cool, cold neutron star. So therefore, it's a kind of a evolving object. It's not a stable one. So when we are considering of parameter estimation of a proton neutron star, it's quite difficult to use electromagnetic radiation because the proton neutron star formed at the center of the supernova. So therefore, detecting the electromagnetic radiation emitted by that proton neutron star is very much difficult because those are absorbed by the outer layers of the supernova nebula. So therefore, it's hard to use electromagnetic radiation. So that's why people or scientists are trying to use this gravitational wave technique to estimate the parameters of a proton neutron star. So as I mentioned earlier, the sensitivity of current gravitational wave detectors are not enough to detect them. So, and also match filtering cannot be used, even though we detect the gravitational wave signal from a collapse supernova. We cannot detect, we cannot separate it by using the output of the gravitational wave detector by using the match filtering technique. The reason is that when we consider about this gravitational wave, the gravitational wave from collapse supernova, it doesn't have a specific wave format. But when we consider about binary spiraling, so it has a very well-defined format. So therefore, artificially we can generate and then we can use the match filtering technique. But in here, we don't have specific waveform for the collapse supernova gravitational waves. So therefore, we cannot use the match filtering technique. Simulation research works are being performed to develop the methods to determine parameters such as mass and radius evolution in proton neutron star. So here there are 2 basic parameters we are going to estimate, mass and radius, because still we are in the initial stage of parameter estimation of gravitational wave from collapse supernova. So therefore, still we are concerned about mass and radius evolution. Why I am considering that evolution? In this proton neutron star, we cannot have a particular radius or mass because this is an intermediate state. It's in a cooling process, and then finally it becomes a stable neutron star. So therefore, in the case of proton neutron star, we cannot determine particular mass or radius. It's a kind of a evolutional process. So in here, I'm going to explain about the difference between the gravitational wave from collapse supernova and binary mergers. These are the corresponding time series, and these are the corresponding spectrograms. So in the case of, so now I'm going to compare these two. If we consider the wavelet format, time series, not specific, it depends upon the explosion, because as you know that we cannot pre-detect how the shock wave vibrate. It depends on that situation. So therefore, we cannot form specific time series artificially. We cannot simulate it. But when we consider about binary mergers, if you know the mass of the binary system and the apart of these two masses, very easily we can generate the or we can define the time series of such a binary system. So, and also, as I told you earlier, match filtering cannot be used because in the case of match filtering, we are matching our artificially generated wavelet and the wavelet embedded in the output of the wave detector. So therefore, it is not practical for the collapse supernova case and it's applicable for the binary merger cases. So in the data analysis method, fundamentally we are using short time Fourier transformation, continuous wavelet transformation, and Hilbert time transformation. Basically, for the scientists are now concerning about Hilbert time transformation as one of the best method to parameter identification for the core collapse supernova. So here I have shown kind of short time Fourier transformation for these two time series separately. So and then as I told you earlier, there are two sources for the gravitational wave from core collapse supernova. One is proton neutron star and one is unstable shock wave. So these are called as Sashi mode and eigen modes. When we generate the 2D representation of frequency time plot for a artificially generated core collapse supernova gravitational wave, basically we can see main two features. This is corresponding to the Sashi mode or the gravitational wave generated by the shock wave, and this trending or this feature related to the vibrational modes of a proton neutron star. So the reason to having this eigen modes is the sudden convention inside the proton neutron star. This is the basic explanation, but there are some density discontinuity and some the fluid variation. Likewise, there are some other processes as well. So when we consider about this proton neutron star eigen modes, here we can see only one trending, but theoretically, by using numerical simulation, scientists have shown that there may be some 3 or 4 possible eigen modes, like frequency trending, like in here. So the frequency evolution is from 100 to 1500. Here you can see that this is the frequency range, and it stays for around few milliseconds, as I told you earlier. In this case, when we consider about this Sashi mode, this is as a result of vibration of standing shock. I told you several times. This vibration of oscillation of this shock can generate gravitational wave. It is in this frequency time up in this area. So the considering frequency range is from 100 to 200, and it also exists in a few hundred of milliseconds. So and then I'm going to consider about now deeply proton neutron star eigenmodes, because I'm not going to deeply discuss about Sashi mode, because our expectation is to determine or estimate the parameters of a proton neutron star. So therefore, I only consider about the eigenmodes of a proton neutron star. So numerical studies shows that there are 3 possible processes to vibrate a proton neutron star or produce gravitational waves. One is F mode, that is actually due to the fluid oscillation inside the proton neutron star. Only one mode according to the numerical simulations. And P mode, actually this is related to the pressure variation or like something inside of the proton neutron star, kind of a wobbling or vibration. In here, there are some possible modes, P1, P2, likewise large number of possible modes in the P. As in the same of P, in the case of G mode also there are some possible modes. This is because of the density variation of the proton neutron star. In this case, you can see that actually contour and overplotted eigenmodes. This contour or the spectrogram related to the artificially generated time series of a gravitational wave from a collapsed supernova, and these overplotted lines are eigenmodes which are generated by using a numerical simulation corresponding to the same gravitational wave by the proton neutron star. So in here we can see, when we consider about the artificially simulated gravitational wave 2D plot, we can see only F mode, but actually it comprises of all this P1, P2 and G1, G2, but our analysis technique are not enough to see or separately identify these modes. That's the main problem that we have, how to separately identify these modes by using data analysis technique, because the resolution of the data analysis technique is very much important in this case. And here also you can see that only F mode can be seen. The other modes are quite difficult to identify. So, and then as I told you earlier, in this parameter estimation, we are mainly concerned about mass and radius of the proton neutron star. So once I mentioned you that proton neutron star is not a stable state, it's a kind of a intermediate state if it evolves. So therefore, there should be a radius variation and mass ratio variation with the time. So therefore, according to the numerical results, you can see that there is a variation of radius and mass. So radius decreases. The reason is that sudden cooling after the supernova explosion, the proton neutron star starts to cool, and finally it becomes a neutron star. I mentioned several times. So, and then when we consider about the mass, it increases. The reason is that even after the explosion, there is a possibility to attract some masses in the outer areas. So therefore, still there is a mass increment after few milliseconds after the explosion. So numerical results shows that these variations. So therefore, we cannot, as I mentioned earlier, fixed mass or radius cannot be estimated. Some evolution of them only can be estimated. So, and then I'm going to explain you the method of parameter estimation by using some few basic steps. Initially, we should be able to detect the gravitational wave time series by a collapsed supernova. So this is related to the output of interferometer. By using interferometer, we record the large number of data, and then if we can separate this kind of detection from a gravitational wave, and then by using kind of a data analysis technique, we should be able to separately recognize the eigenmodes which are comprises in that time series. In here also you can see that only one mode, but there might be 2 or 3 according to this short time Fourier transformation. Because of the resolution problem, we couldn't clearly detect other modes. Here only we can see F mode. But by using some techniques, we should be, if we consider, we can determine or separately recognize these eigenmodes. Then we can go to the step 3. Step 3 is already scientists have generated or established some universal relations between the eigen frequencies and mass and radius. This is one of the simulation work. In that simulation work, they have shown that this relation doesn't depend on the equation of state that they have used. These are the different equation of state and the masses of the progenerator. So therefore, these are called as universal relations. In this relation, you can see that this represents the average density of the proton neutron star, and this is the F mode frequency. It changes like this. I mean, it shows a kind of a linear relationship. Now, if we have this kind of equation, and then if we know the frequency variation, then we can determine the mass and radius evolution. But the problem is that, like in here, at least we should have two detection of these eigenmodes. In here also you can see that they have shown that kind of a nice linear relationship between the average density of a proton-neutron star and kind of eigenmodes, some linear relationships. These are the corresponding equation, and this is the common equation for such kind of relations. These are independent from model and the progenitor, so therefore these are called as universal relationship. It means if we can experimentally detect the variation of frequency, and then by using these equations we can determine the evolution of mass and radius of a proton-neutron star. Actually, in this case, as I mentioned earlier, we should have separately, we should be able to separately recognize at least two eigenmodes. The reason is that in this equation, you can see that these are the unknown factors like mass and radius. So therefore, at least we should have two equation, or I mean, we should be able to separately recognize at least two eigenmodes to get the evolution for mass and radius for particular proton-neutron star. So therefore, it's quite experimentally difficult. I mentioned you that because of some resolution problem of current current data analysis technique, it's quite difficult to separately identify those, recognize those eigenmodes. So anyhow, very recently, one particular simulation research work shows there is a relationship between the average density of a proton-neutron star and the compactness, as well as the surface density and the average density of a proton-neutron star. By using these relationships, if we have only one particular the recognition of one particular eigenmode, then we can very easily estimate the evolution of mass and radius. So these are the current research progress of this proton-neutron star gravitational waves. So when we consider about the main issue, in the case of estimation of parameters of the gravitational wave, as I told you earlier, eigenmodes are located very much closer to each other on the time frequency representation. So therefore, separately recognition of this frequency evolution is important. In here also you can see that this overplotted lines corresponds to some eigenmodes. So in these kind of areas, it's very difficult to separately identify. Sometimes we see as a kind of a crossing area. In this research area, we call it as the crossing nature. So we should be able to separately identify them. So therefore, we should have high resolution nature in the case of data analysis techniques. So conventional data analysis techniques such as short time Fourier transformation or continuous wavelet transformation is not sufficient, but now scientists or astronomers are thinking about some other methods like Hilbertine transformation, because they are because in that case, I mean, in the case of Hilbertine transformation, they are considering about some instantaneous features. So therefore, we can have kind of high resolution than short time Fourier transformation and continuous wavelet transformation. So this is also one another explanation for such a situation. In this case, you can see that P mode and F mode is very much closer to each other in the case of in this area. So when we consider about F and G1 modes, those are located very much closer to each other in this area. So this is the enlargement of the same area. So therefore, this is related to kind of simulation research work to proton-neutron star. But if we get the corresponding simulated gravitational wave, definitely we cannot separately identify these areas. So this is the main problem that we have. So it shows kind of a crossing nature in this kind of places or situation, but we should be able to separately identify them. So this is also one kind of a simulation research work, which also shows that it's difficult to separately recognize those features or eigenmodes by using conventional methods. This is related to kind of a conventional data analysis method. Here, actually, scientists know that there should be two eigenmodes, but in here there is a crossing. But by using these techniques, it's difficult to separately identify them. If we cannot separately recognize these kind of eigenmodes, then we cannot get the frequency evolution of them, and then so therefore then we cannot get the correct mass and radius evolution. So the Hilbert-Hung transformation is one of the consideration as the effective method to avoid this crossing nature in the data analysis techniques. So these are the things related to parameter identification of gravitational waveform for collapse supernova of a proton neutron star. So these are the articles that I have written to InSAR paper. This is the 2021 article. This is the basics related to gravitational waves, in the gravitational wave. So if someone interested in this article, then I can send, but it's totally written in a single language. This is the very new article which is written to the same magazine. So in here I have explained the things that we discussed today. So I mean how to estimate the parameters by of proton neutron star by using gravitational wave. These are the things that I have done in recent past. So thank you very much for listening. I think that you might get kind of idea. Maybe it's difficult to explain everything related to this kind of deep research within 1 hour, because there are so many things to study by ourselves also everything cannot be explained. I'm very happy if you get a just rough idea how to do this estimation, especially how do we use the mesh filtering, because that is very interesting thing. So if you are going to do higher studies related to gravitational waves, these things I think would be very much important.
Yes, sir. Thank you very much. So, dear participants, if you have any issues, now you can raise your questions.
If you are ashamed to ask a question in this session, no problem. If you have any problem related to today's session, you can send an email, ask some question related to today's session, no problem. But the problem is that my time schedule is very much tight. Maybe replies might be quite delayed. But anyhow, I will try to explain or give the answers for your questions.
Okay, everyone, I hope everything is clear to you all. So, before winding up the session, I would like to express my sincere gratitude to today's expert personality, Mr. Malitem De Silva, for allocating your valuable time. Thank you very much, sir, for the effective session. It was actually very beneficial for all of us. And thank you, Dr. Leon Fernando, for helping us to proceed with our plan. And also, I'm very much grateful to all the participants, since your presence here is a tremendous support which lead towards session to success. So everyone, until we meet again, stay safe and good night.